Hello everyone, welcome back to another video from my Chem Corner. In today's video, we're going to talk about another topic from the chapter Solutions. So before we move into the video, if you're new here, please don't forget to subscribe to the channel and hit the bell icon so you receive notifications as and when I upload the video. So without further ado, let's move into the topic. So in today's video, we're going to talk about ideal and non-ideal solution. But before we move into ideal and non-ideal solution, I would like to relate this particular topic to what you learned in first year. So in first PUC, you would have learned this chapter called States of Matter, in which you've learned about ideal gas, right? So we had certain laws that were governing the gases. And we said that if there is a gas that obeys all those laws, then it's called as an ideal gas. So same way here, you will come across something called as ideal solution, which means the solution that obeys a particular law over all concentrations, that is going to be called as ideal solution. So the concept is very much similar to that, although the topic is very wide and different from what you learned last year, but you'll be able to relate that it's no different from states of matter. Alright, so here under ideal solution, we say that solutions which obey Raoult's law over an entire range of concentration is called as ideal solution. So there's Raoult's law that's governing the solution part. When you try to say increase, decrease concentration or try to increase the temperature and all of that. So here if a solution obeys Raoult's law over an entire range of concentration, it's not just fixed to a particular concentration, it's going to be to an entire range of concentration, then we call them as ideal solutions. Now for an ideal solution, the enthalpy of change for mixing of pure component is going to be 0, which means you really don't need an energy to mix that particular solution. The energy is going to remain 0 because it's a pure component. Similarly, the volume is also not going to change. It's going to remain the same. Now this means that there is no heat evolved or absorbed during mixing of two components. So you take component 1, you take component 2, you're trying to mix them. There is no particular heat evolved or heat absorbed during the entire solution. Therefore, we'll try to say that the interaction between component A and A, two similar components, is similar to the interaction between A and B. So if I take say A and A component, which are the same compounds, when I try to mix them, there is no change. So if I try to take say a HCl solution and try to mix the same concentration of another HCl solution, the concentration is not going to change. There's no much of heat evolved or heat absorbed because they both are same concentration, same compound. So whether I'm trying to mix say HCl with another solution or HCl and HCl, we say that for an ideal solution, there is no much change in anything. The energy pattern is not going to vary. It's going to remain the same itself. There's no difference in it. So that means to say perfectly ideal solutions are rare because we've all learned that when we mix two solutions, there is at some point energy evolved or energy absorbed. So to find a perfectly ideal solution, it is a rare concept. Now an example of a solution that obeys nearly ideal behavior, we can't say an exact ideal behavior, but nearly ideal behavior, is a mixture of N-hexane and N-pentane or a mixture of benzene and toluene. These are nearly ideal, they are not ideal perfectly. Alright, so if you are asked to draw a graph for an ideal solution, this is very much the same as the graph we learned under Raoult's law. It is the same graph here that you learned for an ideal solution. Now, when you're talking about ideal solution, you have something else called as non-ideal solution, which means a solution that do not obey Raoult's law. Not all solutions are ideal, right? So there are majority of solutions that are non-ideal, which means they don't follow Raoult's law. So they are called as non-ideal solutions. Now, when we talk about non-ideal solution, which means there is some sort of a deviation from Raoult's law, right? They're not obeying Raoult's law. There is some factor. So that way we can classify them based on positive deviation and negative deviation. So what do you mean by positive deviation? So I have a graph below here. The dotted line in each of this graph is talking about ideal solution. So first point clearly says if the vapor pressure is higher than ideal solution. So in the first graph, if you see the vapor pressure is higher, which means to say that they are having positive deviation. But in the second one, if you see, there is a downward curve, which means to say that it is lower than the ideal solution. Then you call them as negative deviation. Now when you talk about higher curve in this case, or higher vapor pressure, which means the interaction between two components are weaker than their pure component. Okay, so if I'm taking A and B and trying to form bonds between them, that interaction is much weaker than they were in their pure component. So which means to say, because the interaction is weaker, they prefer to escape as components itself, because they want to be in the component state, because when you try to bond them, they're not bonding. The bonding is very weak. So that bonding can be broken easily. They'll come back to their component state itself. So there they prefer to be in their component phase itself. But if you're looking at negative deviation, because the vapor pressure is slightly lesser, between A and B there is a strong intermolecular force of attraction. Because of that, they don't escape as components very easily. Because the bonding is stronger, they prefer to be bonded in the product state. Now when I'm talking with respect to enthalpy of mixing and all of that, because the bonding is weaker and you want them to form bonds, you need to apply more energy, more enthalpy of mixing is required, because it's not mixing, it is not forming bonds. So what you need to do, you need to apply more energy. That is why the energy is greater than 0. But in this negative deviation, what is happening? They prefer to stay bonded. They want to stay bonded as products between A and B. So here you don't have to apply more energy. So the energy can be lesser than 0. A classic example of a solution that shows positive deviation from Raoult's law is a mixture of ethanol and acetone. Now here in this case, the hydrogen bonding can be easily broken, and they prefer to be as ethanol separately and acetone separately. Whereas in the negative deviation, they have a bonding between phenol and aniline. We all know phenol is a proper acidic in nature, aniline has a good basic in nature. So because they share that lone pair and the acidic proton, they have strong intermolecular hydrogen bonding. Because of that, they prefer to stay as products and not as reactants. So here this is a classic example of a negative deviation from Raoult's law. Alright, so these are pretty much the differences between positive and negative deviations. A 3-mark question in your exam. They can also ask the graph, to how to draw the graph, so you should be able to draw it. Now the next topic that we're talking about is azeotropes. Now what are azeotropes? These are mixture of liquids having the same composition in the liquid or vapor phase, and they boil at constant temperature. So that is a property of azeotrope. They have two types. One is minimum boiling azeotrope and the other one is maximum boiling azeotrope. Now what do you mean by minimum boiling azeotrope? If you have solutions that show positive deviation from Raoult's law, then you call them as minimum boiling azeotrope. Maximum boiling is the ones that show negative deviation from Raoult's law. They are called maximum boiling azeotrope, and they have individual examples for each of this. So this is again a 3-mark question. They can ask define azeotropes, classify and give an example for each. So these topics are smaller, but they carry a lot of marks when it comes to writing your board exam. So kindly focus on these and learn them in detail. So I hope this video has been helpful to each of you, and if you have any doubts or any suggestions, please don't hesitate to drop an email to the email IDs given in the description box or a comment in the comment box. I'll see you in my next video. Till then, take care.